Hello everyone, today we'll talk about the problem kth smallest prime fraction. Pretty weird title. We're given a list of integers starting with 1 and containing then in increasing order some prime numbers. Now, when we take a number from that array and divide it by a number that's later in that array, we get a fraction that's less than 1. And we want to, among all those possible fractions, so array of I divided by array of j, for I less than j, return the kth smallest in the form of numerator and denominator. Now, one easy way to solve this problem, and the one that I would probably recommend, is to just don't try to come up with anything, special, anything even remotely interesting concerning this setup. Just create all the about n square possible fractions and return the kth of those. And the easiest way to do that would be to just create all of them, sort them, and return the kth in that sorted list. So this is the code that implements it. We just create all the fractions, we sort them, and return the kth. Now, when it comes to comparing fractions, I think it's a better idea instead of when, let's say, we have a fraction. So here a divided by b, here c divided by d, and you want to compare them. So it's probably a good idea to compare something like this instead. So we simply multiply by both of the denominators. So we get AD, CV, and now we have just multiplications instead of divisions, and we don't have to deal with any precision issues. So that would be, I think, a better idea. So this is what I do here, and of course, if we want to compare elements, and then this is a non-trivial comparison operator, so it cannot just, as we would normally, write it as a very simple key, or at least, I don't know if it's possible to do so. But there is a function in functools, so available by default here in LeetCode, CMP to key. So if we have a standard comparison function, which is essentially just subtraction of two elements, then we can define what we want here. So here, when we want to compare two fractions represented as a tuple, right, as a pair of numerator and denominator, then we just take here what's above times what's below on the right. Same thing here, but swapped. We subtract them. If you never thought about that, comparison is very similar to subtraction, and that's often how it's thought about on low level, because this will give us a positive number if one number is greater than another, negative if it's the other way around, and 0 if they are equal. So those are the two values that we expect from the comparator. And of course now we can turn that comparator to key by this function. Also, as a side note, it's quite an interesting thing so you might want to think about how you would implement this function. So you would implement a function that takes a function that compares two elements in an arbitrary way and turn it into some function that takes a single element and returns something that when you compare with what it returns for another element, that comparison is exactly this. So anyway, we just have to sort it in a fancy fashion. I recommend avoiding division, so this is why I do it like that. Fractions are represented as a pair of numbers, and of course we just have to return it as a list, the k minus first, right? Because k starts from 1, list starts from 0. So that is the simplest solution. And of course, here, this is O of n squared, also times log of n squared. Log of n squared is of course the same as log of n, but still this is even worse than n squared, but it is a solution and it passes. One easy way to improve the complexity here is, of course, since we are only interested in the kth element, to use just some selection algorithm that will return to us the kth smallest element. Because of course there is quick select, there is the median of medians algorithm. I'm not sure if it's easily available in Python, any implementation of those algorithms. In C++, you have the function nth element, right? So in C++, you should probably here use nth element. This is floor, right? So that would make it, not need the sorting, but instead just finding the nth element, so that would be n squared. And now there are also other solutions, but I'm not sure if they are significant, especially they may perform well depending on the value of k. And those require some observations about the structure of this resulting array. Because one thing that we can notice is that if this array consists of the same, let's say, numerator divided by different denominators, then if this a here stays constant, and we take here b1, then we divide by b2, and so on, and if those are increasing, then those fractions, right, so if this is greater than this, and this is still a, are also in a sorted order. So that means that we can, for instance, use binary search. And in that case, we would, let's say, define for ourselves the value of a fraction that we guess would be the answer. And now for every numerator, we can look for all the possible denominators. And since they are in a sorted order, those values of a fraction are in a sorted order, then we can find in logarithmic time the position at which, for instance, the last position which is smaller than our guessed value. And now everything to the left of that position, or in this case if we were thinking about smaller to the right of that position, would also be smaller. And in that case we can just count all of that, and if we get exactly k, then yeah, that first number that is smaller than that would be the answer. So we can do binary search like this, and it would take some implementation. And another way, which is more, I think, natural because it's also a common problem, is that since we have here n lists, and those lists are sorted, then have you ever thought about how you would create a sorted list from n sorted lists by merging them? Because typically, for instance, when you implement a basic merge sort, then you merge two lists. And it's very simple, you just compare the head of those two lists, and that's all you need. And when you try to merge k lists, then that comparison can become the bottleneck, and the standard technique is to use a priority queue to speed it up. So this would be the code that implements it. Instead of maintaining all, especially not sorted, all of those possible pairs, all of those possible fractions, we only remember the fraction 1 divided by array of j, right? So the smallest fraction where the denominator is equal to array of j. So that would be only n numbers at the beginning. The way we compare two of our fractions is the same, so we just do the same thing where you multiply crosswise. But now, since we only maintain in a priority queue those n numbers, we can take, we are guaranteed that the smallest fraction is one of those. Because all the others would have this denominator be smaller, right? Or the numerator be larger. So that would increase the fraction, right? So if k is equal to 1, then the smallest element on that heap, so the top of that heap would be the answer. And if it's not equal to 1 but something more, then we just can immediately discard the top element. So we essentially just pop the top element from our heap. Now, if it's possible to increment the numerator to the next one in order, then we do so. It's impossible when I plus 1 becomes equal to j, because that means that we have run out for that denominator j of all the possible fractions, so we don't do anything. Otherwise, we just push it back on the heap. And after all those, what's on top of the heap is our answer. And here, when it comes to implementation details, so I'll just keep indices, so index 0, index j for the possible later j's. So for comparison, I will put array of left-hand side of 0, not just left-hand side. So this is to show that it's possible to implement it like that, because here I implemented just left-hand side, right-hand side, because those are values, not indices, and here they are indices, not values, so array just goes here. Very simple. And also, instead of thinking about how to try to force the priority queue to use our comparison operator, our key, one trick that we can do is just to create as values not this raw tuple, but instead just calculate the key for ourselves and insert it as the first element, so that will be used as the basis of comparison of all our elements. Of course, here for priority queue, I use heap queue. There are other options. So this is an example how to use heap queue. You heapify a normal list. You can heap pop, you can heap push. So those are the basic operations on priority queues, or otherwise known as heaps, because that's how they're typically implemented.